Hello, everyone. I'm very honored to give a talk on behalf of my team. We work between UCL and Aston University. The title of the talk is called The Knowledge Graph and Deep Learning-Based Text-to-GraphQL Model for Intelligent Medical Consultation Chatbot. We are published in Information System Frontier. It's a Q1 and also ABS HHG3 journal with a link here. And I'm going to talk about the background and literature, followed by our methods, results, and analysis, followed by the conclusion. So in terms of background, as we know that we work with lots of data, with lots of users, and there is a need to work with surgeons, medical researchers, and other training and doctors from different hospitals and different institutions. So there's a need. With a lot of the data and knowledge has to be better managed and in a simplified form, because with lots of papers and documents to read will take a lot of time. And even we have some existing system, it may not be the best solution, because we need to have systems to simplify our work and to sum up our work. We don't have to go through reading at once, and sometimes even you have performed some surgical task or some medical task we may even have forgotten. Therefore, we need a system that can translate those documents to something we can understand, but also we need a system that can answer queries. Even if you are training a doctor, sometimes they may not even know certain knowledge and you have to train them. Therefore, the kind of system that will allow the knowledge to be easily disseminated, and then you can pass on. So medical QA system scenario, we need to use it in hospital guidance and receptions to deal with a large number of patients and lots of queries in and out. We have a system in place, and we have an online medical consultation, because in some countries, you first of all see your doctor through online consultation. So you need some kind of medical chatbot to deal with the queries and ask all the questions, such as your date of birth, your name, where your location, and which medical clinic you are attached to. Then we should have some dialogue system and a medical automatic diagnosis, because the chatbot will be able to deal with some basic level of image processing. However, we face a challenge there. We need more complex systems, such as from rule-based QA template methods to a neural network-based pipeline method. Because why? We have a lot of data, and also we have different patients with different type of symptoms. And then you may also find that a large number of information and documents have replication, and there are also similarities. We need to categorize them. We need to make better sense of the data. Therefore, neural networks, an AI-based method, will be always extremely helpful. And then we can replace the previous simple matching model, so that we can perform more complex text representation, such as retrieval, matching tasks. And even in the future, we can make a better prediction. We can even predict what will be happening. So this will be having a step-by-step approach. And the motivation, first of all, there are always new methods. In this case, and then look at two methods in particular. One is called neural network-based pipeline model, because by using a smart algorithm, they will allow us to work together. And pipeline models ensure that we work step by step, one at a time, and then to ensure that we are doing things correctly, step by step. So this method will allow us to reduce the drawback of a semantic analysis of regular expression template method implemented in the form of simple matching. Because if you rely on certain technique too much, you may be also biased. So that we're using the neural network approach will be allowing us to be more independent and fair, and then it can provide a new breakthrough opportunity for technological development. In this field, knowledge graph, as we know, there's lots of document or there's lots of data, and sometimes they're unstructured data. You may not even understand what they are, and you need even to spend time to structure the data and to even clean the data. Therefore, if we can present the results in terms of graphical forms, then we can have a better understanding. Therefore, knowledge graph, KG, provides intelligent dialogue system with continuous updated external knowledge source. It then can create a more flexible and extensive expansion of the neural language question and answer system, because we need something that can answer our need, and we need an interface that's user-friendly. We need an interface that can allow us to see the result within seconds. Then integration will be crucial, because why? Each method has its own strengths and weaknesses. We need both methods to work hand in hand so that we then can have a better understanding and make a better usage, such as the knowledge graph, such as the neural network-based component will allow us to perform our tasks well and also accurately. And the performance of dialogue system in terms of the domain adaptability, recognition accuracy, interaction quality can be improved from levels of different modules. So we then look at those factors very carefully. And by integrating, the method will allow us to strengthen what we have. So I just come to the literature first. The literature will allow us to understand, but please read our paper, because a lot of information is on our paper. The purpose of this talk is to allow you to understand what are the important messages. So text-to-SQL tasks, because there are already many research papers and projects on understanding how we can make a text-to-SQL task so that we can make a better and quicker queries. But also there are rule-based and deep learning-based dialogue system, because by having the rules, then first of all, it then allows the people who input the data to follow the rules, so that it is much easier to then retrieve the data afterwards. And deep learning will allow us to understand what will be the patterns and then categorize them, and then we can also make a better match and also a quicker retrieval. And rule-based NLP and semantic parsing tasks, which means that you create the rules. For natural language processing, of course, there are also some ways to construct your sentences and grammar. Maybe you can also limit your input cannot exceed like 10 words or 15 words, or maybe you have to type in certain keywords. Then corpus-based NLP and semantic parsing tasks, of course, there are also methods that try to combine different advantages together, so that by reading our paper, you will then know a lot of detail. Please read our paper and cite our paper. Then now I'm going backwards, just talk about a brief introduction. What the others are doing, because the brief intro, the text to GraphQL, in a way that text to GraphQL is the task of converting one user or the user's questions into GraphQL, because it's not only for the SQL, but then if we can then make a next step forward to make them into GraphQL, so that the graph query language, when a graph database is given, because nowadays we work with graph database more, and we need the data to be in a graphical way, so that we can then retrieve the information much quicker and easier. And this is a task for the semantic parsing that transform the natural language problem into a logical expression. As you can see, this is example. What are the names of COVID-19 specific drugs? And then we then can concatenate, which means that you find a lot of keywords. You then find them, combine them all together. Then usually it's quicker and better to do it in XML. And then the output will then make them in a more structured way, such as this is the end result of the query, the disease with a name. What's the name of that? And also what is the drug or the treatment for this? And then the existing related work focuses on text-to-SQL tasks, and there is no available semantic parsing method in the dataset for the graph database. In order to fill the gaps in this field, then to serve for medical human robot interaction better, we propose the task and the pipeline solution called the text-to-GraphQL task. There are not many researchers doing this, and we are very fortunate to be one of the very front runners, and we are going to introduce more details later. Then, as you can see that, the methodology, we have to introduce what the external knowledge into the model. So in this case, we have a thing called the language model. So we first of all use adapter. So adapter means that we pre-train it with the linking of GraphQL schemas and corresponding utterances, so that the adapter then understands what the needs for the GraphQL and the schema. Of course, there's certain techniques or certain schema, and in fact, all different NLP or different text matching techniques that will require schema and corresponding utterances. What are the specific things we need to know, and what are the keywords we need to look after, and what sort of categorization we are dealing with as external knowledge introducing in a plugin. So plugin means something that can very easily attach to and then check to and also work together, such as in this model with the input token, then comes in, and then in the input token, then we can follow this. There are keywords based on, for instance, in this case, we have to type in disease and type in what you are looking for, and also the treatment for that. So there are also keywords associated with it. For instance, if you say travel, it means that you have to say where you are and your destination and the method of travel. So in this way, you have the language model together with adapter. So with the adapter, then can double check with this. So the advantage of doing so is allows you to map between a logical language and a natural language, so that you can have the benefits of both methods to then get a faster and more accurate, because you need to then target to your destination more directly with better realize the end-to-end human-machine language translation task. Then both are going hand in hand. Then when you double check that, you can then concatenate, so that when you concatenate, we have better outcomes. Then you can use an encoder as the final output. So when you get further, it may go a little bit complicated, but please just bear in mind that it's because it's new, so that we want to show the worthiness. Therefore, it's worthy of your time to start our paper and consider using our work to resolve the existing issues. So adapter, we can use that very effectively with a language model. So the mapping between a logical language and a natural language can be introduced faster and more directly to better realize the end-to-end human-machine language translation task, so that you translate what is there. So you translate the adapter. The adapter then gets to different language, and this is what's inside the adapter. Inside the adapter, you can see that first of all you have the DAO protection layer. Then it goes to a transformer layer, and then it goes to a protection layer. In the transformer layer, it then have the bottom-up approach. Then it has the multi-head attention. Multi-head attention means that you now find the major keywords that you guess to. Then you add a norm. Then feed them forward. Then you find the better category. For instance, pizza then is categorized in food, then you put them in food. Yeah, this is one of the example. And then this is the language model. So in the next slide, I'm going to show what's inside the language model. So in the language model, you can have the input, token embedding, semantic embedding, position embedding. So input means that those are the words that you put in. And with the token embedding, it means that what are the keywords that you are trying to categorize to. And the semantic embedding means that like you belong to which type of category, and then of course the positioning embedding then will find a more suitable places that your matching will belong to, so that you have 3 types of checking, and you need to fulfill 3 combinations or 3 criteria, so that your queries and your matching are more accurate. Because if you are just match on the same string, you may totally use up another different word. Or if you just look up the dictionary, and it's probably not reliable. And if you only check on the existing sources, if you come across a new word, your model may not be able to process. So having 3 will be at least giving more assurance to work with. So that when it gets further, this is called a pointer network. So pointer network means that when you have so much data, you have to then not only to query and also to process data, but also when you have the outputs, you need to find the most suitable places and then send that to your appropriate destination. This is called pointer. And pointer network means that inside this network, we then have the way to identify where you are, and then therefore we can then have some our smart mechanism and algorithm for this. So this is called pointer generation. So first of all, when we have the data, so what is the name of a COVID-19 specific drug? So each word has been processed one by one. So then it comes to the next one is called attention distribution. So attention distribution means that if there are some keywords that have a greater weightage, then we then pay more attention. But of course, we can start with some initialization, you know, or maybe we can put certain emphasis on certain things. In medical domain, especially during the COVID time, then COVID is the most hit words, and also the symptoms associated with it, and also with the treatment, and also together with the patient's detail. But then when we have going to the next step, we have then 3 other steps. Fields and omens attention, schema attention, and decoder state. And attention means that there are some specific way to deal with the processing, and so that we then can have a better categorization to put them into a better matching. But then also decoder means that we're trying to get outputs. So how do we do that? First of all, we can use a guide, which means that it's a summary of the results or recommendation based on previous experience. Then we can have the process to then start the generation. The generation then comes into a series of mathematical formula in our paper. Please read our paper, and then we'll then explain the details. Then when we have transformed the different data, in this talk, I'm trying to use very easy language for you to understand, but for some expert-based type of knowledge, please read our papers. And then we'll find that there are ways to perform a better function, such as a graph transversal. So graph transversal means that it's a step that begins to make the text into the graphical form. Then before we do this, we have to have certain intermediate stage. So we can consider these are the intermediate steps. So before we then become graph, from text to graph, you cannot just have a jump just like that. And so we have them in place. So for instance, in this case, that we have the query disease name, COVID-19, and the drug. So then in this example, we use disease drug. But of course, you can then fine tune that into disease treatment, or even congregate them more with more combination. Of course, more combination will have more complexity. Then in this case, then if we do 1 to 2, yeah, so 1 times 2, then you can then have the result in S and E, so that you then can record them much better. Then you can perform the experiment to see how it goes. So GraphQL schema attention is the one to match the encoder output to all the schemas in a vocabulary in computing attention distribution. So then we can focus on certain vocabulary. And attention distribution is used to determine which GraphQL schema are mentioned as the corresponding utterance. So then once we know it, then we will be able to find and then go forward. And also the field and argument attention, there can be some other special expression to annotate what we are going to do. So this is our pointer network and pointer generation system explained in our paper. And please read it. And then getting further, what we are going to do is that to make things in structured way, we then copy the object's token for utterances to generate corresponding graph QL statements from the graph database retrieval. And then we build an adjustment mechanism to get the final output and with the improvement. So this is a source input utterance, which means a sentence or certain sentences. Then we have the XLM. Is a kind of XML-based language model with adapter that we have explained earlier, and then we perform the pointer generation and pointer network, the one that we explained. Then we can get the results. Then we can also have the target output. So because in order to get a target output, we also have to have GraphQL statement embedding, so that when we have the embedding, we will be able to use a transformer decoder to do this. So this also involved with 3 steps, such as self-attention, the DAG, and it means that decoder, encoder, and attention, and FFN, just another way to transform. So then we can get a outputs in 2 ways. One is to point back to a pointer network and pointer generation. The other one is for linear and softmax functions. So in a way that this adjustment mechanism allows us to use this example. For instance, the source, the COVID-19 specific drug, then the names for this will goes to the drug, and the COVID will comes to the disease. So when we have this query, this is in the form of the graph query. Then we then copy objects token from utterances, and then we generate the corresponding GraphQL statement. So that when we have, first of all, we then have the conversion. The conversions has been explained in the last few slides. So from the source text to graph query, and then once we have performed the right task, then we generate the statement from and also within the GraphQL. So when the graph queries, you can see those statements. So knowledge graph is one of the representation that has been commonly used, because that in medical field there's just too many records and too many keywords, and also there are a lot of terminologies we have learned, and even there are some other languages, especially Latin. So this will mean it's just creating thousands and even millions of complexity, and it's even adding up. Even just when COVID came, then we have to add more terminologies, findings from other medical investigation, and also from other countries' lessons learned, like what sort of vaccine will be useful, and what will be the percentage of successful treatment. But then we have to use a data set. This kind of data set is also hard to find, and the one way we use is called 39.net. That's from China, and then we based on medical questions and answers for the data collected from this side, because there are also a series of questions and answers that we need to do. So for the training purpose for the machine, then we then use the existing data set just to train the machine to be able to do simple tasks with a very high level of accuracy. So in this case, that we can see that the nodes that can also represent treatments, departments, medicine, and symptoms, and with associated with diseases. So that there are different things, they are linked to each other, which can mean, for instance, this doctor is treating a number of different patients in different departments, and then he or she is using certain drug for treatments of COVID-19, and so on. So then we can describe all different cases, because they will get lots of information. So that with the graphical interfaces will allow us to simplify a lot of complexity. We don't have to pull in so much data. But of course, if you have a very strong graphical database, then when you click this, will show more information for you, then to guide you what has been happening and what has been done before. Then the relationship type is to build a linkage between different, for instance, different doctors or different practices of treatment, or between different usage of medicine. So that then create an interaction with people, so that we then can organize everything we've done into knowledge graph, because the knowledge may mean a series of actions you've done. It may also mean the things you have studied. It may also mean some meaningful result you have undertaken, whether from surgeries, whether from other practices, or your own practices, or from your own experience, or even from some medical studies. Therefore, we then need to build this and then get everything together, and then use the text-to-GraphQL middleware as the example, so that we then show everything as a knowledge graph. And the Neo4j GraphQL library is the one that we use the cipher. So then we'll then show everything like this. And then we have the natural language text queries as an input, and as the logical expression as the output. Then for details, please read our paper. And result analysis are as follows. Then you can see that the results. We then use our own methods, as we have explained before, and then we compare with other people's results. So to see whether how it works, and also the performances and issues we have. As you can see, it's very hard to achieve, even with 70% above, because there are a lot of ground level work and a lot of unexplored territory we need to know. Therefore, under the testing circumstances, we achieve 76.2%, and then with development 75.8%, and test slightly lower. But then we are always in the process of making improvement. And this, on the right hand side, these are the results of our methods compared to others. So then we then show the result in terms of 3D, so that you can see the results between 50 plus to 70 plus. And then we are on the leading ones. And similarly, the accuracy, we are also having a better accuracy compared to other comparative results and methods. And then the second type is on the result analysis for our methods. We also compare our methods with other people's method. And as you can see that there are two different experiments to be used. So one is called ATIS. We use that one of the researchers' work as a cross comparison with others, and then GeoQuery is from another group of researchers, but then their focus was to convert into the graph query language. So then we compare our work. When you're only focused on ATIS, we have 80.4%. It's only the second one after one of the competitive methods. And then with GeoQueries, we achieved 63.7% because there's a very large extent of errors, and because during the conversion, there could be things that they're not getting well, and also the query may not, even you get things right, you may not query correctly. So therefore, even achieving 60% above is pretty difficult. As you can see that only two methods, including our method, they can achieve that. And other methods without using it has achieved a very low percentage of the accuracy. But also we then use 39.net medical Q&A text to GraphQL dataset. So then we use our dataset. So we use the dataset with our own proposed method, and then with adapter, and then without adapter, we made the comparison. Then we show the results that we can always achieve up to 75.6% for execution accuracy, and then exact set match accuracy is 76.8%, which means that when you get an exact match, but even sometimes when you get an exact match, it may not be fully executed because there can be due to various reasons. Maybe the text is too long, or maybe you're doing a lot of processing and so on. So that at least we can achieve 70+%, and the results show that it also shows the consistency between our work compared to others' work, and then and so on. And if you can please read our paper, it will show more details. And the conclusion. Sorry, there are different meaningful summaries as follows. So first of all, we propose encoder-decoder pipeline composed of a language model with a schema utterance knowledge introduction mechanism and a pointer network with complex computing mechanism. Among them, we then have inserted the adapter layer pre-trained with the schema utterance knowledge in this language model, and the entire language model can be regarded as a smarter encoder of the whole pipeline, as we have explained in the diagram, and to show you how it can be done. Then this allows the encoder to use the rich language, natural language knowledge in the language model, and the matching knowledge of the schema corresponding to different utterances to perform a more accurate logical formal translation of the input natural language query. The improved pointer network as decoder can use the attention mechanism to calculate the weights of the content vector of the logical form sequence input by the encoder, and use the guide mechanism based on the GraphQL schema dictionary to restrict the distribution of the weights in a corresponding reasonable range. Then we explain how the pointer network works, and then together with the attention mechanism, so that they can point to the right place and to get a GraphQL schema. Then we can use the calculation of weights and probability distribution, the token output, and each step is determined, thereby forming the output of the complete GraphQL statement sequence. And the research is verify the practical ability of the model by testing the execution results of the 39.net medical Q&A knowledge graph and derived dataset, which includes natural language questions and corresponding GraphQL queries. And through the comparative experiment of Spider 1.0, ATIS, GeoQuery, the effects of the generalization ability of the proposed methods have been proved to a certain extent. As the first work of the Text-to-GraphQL, this will provide some enlightenment for the development of this field, so that we try to demonstrate our pioneering approach. So, of course, there are limitations. One of them is the lifelong learning will be used to further realize the extractor of the information entities relationship semantic structure of sustainable learning to better realize the expansion of the continuous increment knowledge graph and provide more knowledge accumulation for the question and answer system. Furthermore, the specialized medical domain language models will be used for higher performing text-to-GraphQL models. Autonomous methods such as deep reinforcement learning, it will be combined with crowdsourcing and other methods to be used as schemas, and there are various combinations to match more corresponding utterances. Limited by the lack of the available graph database as execution support for the dataset converted by Text-to-SQL. The proposed model cannot be verified on Spider 1.0 in terms of the execution on the real graph database. Similarly, since no other methods are available for text-to-GraphQL tasks, up to date, the proposed model cannot be compared to the 39.net medical question and answer dataset. This will also be the key exploration direction in future. So what you cite our paper? First of all, is one of the first work that proposes the text-to-GraphQL task and provide solutions and resources for it. And it's also one of the first work that provides method to convert text to SQL data into GraphQL format. The model introduces adapter mechanism to introduce domain knowledge into the language model, which is more efficient and convenient than the previous mainstream method of directly pre-training the language model, and can be quickly hot plugged into other language models. The adjuster mechanism designed for the proposed model can also be used to make corrections to bring a more accurate logical form sequence output for generating the pointer network. So please, if you can consider citing our paper, if you find our paper and also our method relevant, helpful, or inspiring to you, because we always try our best to show you the innovative and also very new breakthrough methods. So the link of our paper is here. It's free forever for you. Yes, it's free forever for you. And thank you so much for your time. And we wish you all the best. And we will meet again in the near future. Thank you.